Turn this on.
Is the lid so like no dust or any microbes get in there?
No, the lid is because you have the electrodes here.
Okay.
And you have to connect it some way. And this gets a little bit hot, so it tends to evaporate. So the lid prevents like the liquid to go away and just stays there and then drips back down.
Got it.
So we can leave this, and I can show you. I can give you a small lecture. You just saw me make. It's because we want to separate stuff by size, and we also want to visualize stuff. So you've done PCR. So you have your tube, your PCR tube after the PCR reaction, and you want to know if you have stuff that actually got amplified in your tube. So, and you want to know if it's the correct stuff. So let's say you're trying to amplify a gene. So you have your, this is the genome, let's say, your gene is this one. So you use primers, one here, and this should be, let's say, 1,000 base pairs. So you run your PCR with your primers inside the tube, everything like supposed to be working fine, and then you want to know if you do have that piece of DNA that you just amplified. So that's why we run a gel. So you make a gel. The gel is made of agarose.
Is that similar to agar, or is it just?
It's the same thing. It gets you get it from the same place. It's an algae that gives these polysaccharides. But agarose, it's more refined. So I'm going to show you agar and agarose so you can see the difference visually. They are the same thing, but one is more refined than the other one.
Got it.
So gel. So DNA and RNA, they both have phosphate groups, PO4, and these have a negative charge. So you're gonna have your nucleotides bound by this phosphate backbone, and all these phosphates have negative charge. So DNA and RNA both share the same quality, that they both have negative net charge. So if you have a negative charge and you run a current through a matrix, in this case the agarose gel,
you're gonna push it away.
You're gonna push it away, exactly. So the negative is gonna go to the positive side. So positive side should be on the end, on one end, and here you're gonna have the negative side of current. So those wells, that's how we call them, well. They just saw me fill up with the blue liquid. That's where you're gonna put your DNA or RNA, and then you're gonna put it in that gel rig that we call. Apply a current through it. The current is gonna go this way, so your RNA is gonna go. Your DNA and RNA are gonna go this way, right? So this is like a matrix, like netting, something like that. So you're gonna have pores, bigger size pores, smaller size pores. Anyway, your DNA is gonna travel through those pores, and if it's a small molecule, it's gonna travel fast, and you're gonna end up here. If it's a big molecule, it's gonna travel slower, and you're gonna be right here, right?
Right.
So we have molecular markers. I'm gonna show you that. So basically, so you run the gel. After that, you want to see what you have. So that for some reason we use ethidium bromide. Ethidium bromide binds to these nucleotides, like intercalates between the bases. So you have your 2 chains of DNA. It's gonna put in, like, inserting itself here, and when it inserts itself into the DNA, it's gonna glow when exposed to UV light. And you're gonna see that. We're gonna see that in the UV light thingy. So one other thing we do, we run a molecular weight ladder. This is the ladder. That's how we call it. So you're gonna have molecules of sizes that you know, and you buy this. So I can show you here. So we buy those. They sell it commercially. And this is the kind of the map. So the one we're gonna use today is the benchtop This one, 1 kb benchtop, 1 kb DNA ladder. So this is the size that that you have in here. So 6,000 bases, 5,000 bases, 4,000 bases, 3,000 bases, and so on, up to 250 bases. So you see, the bigger sizes are on top, and the smaller are on the bottom, because you run that way, and the bigger molecules are gonna travel slower, right? So the reason that why we use that is, like, in the example I just gave you, like, for example, you have this gene that is 1,000 base pairs. So when you do your PCR, you run a gel, you want to see a band right in the 1,000 base pair marker. So let's say here you have 6,000, 6 kb, let's say 5 kb, this one. And this one right here is 1 kb. 1 kb is the same as 1,000 base pairs. K is for 1,000. So you want to see a band right here. So if you run your PCR, you run a gel, and you're expecting to see a 1,000 base pair product, and you see this in a gel, you pretty much can guess that you have whatever you're expecting to have. On the other hand, if you run the same gel, like you do the PCR and you run a gel and you get a smaller band or a bigger band, something happened with the PCR. So maybe your primers are bad, or your template is different, whatever. There's a problem. So you can see well, there's a problem with my PCR. It didn't work as I expected. You can troubleshoot. You can change conditions. You can change primers. You can change a bunch of things. So the gel is sort of like a way to analyze what you have and see if it's right. Maybe you can. Or wrong, but maybe sometimes it happens that maybe you have the band size that you were expecting, and you say, okay, this is what I wanted to have. You keep working with that, and at the end, when you actually see what you have in there, it's not really what you wanted on the first place, but that's a different story. That's usually not the case. Okay, so this is the basics of the agarose gel. In the lab, we have three type of rigs I can show you. So we have this big one, we have the small one, and we have the medium one. So the size that you're gonna use depends on the amount of samples that you have. Like for example, the small one uses this gloves. Everything here you have to assume is contaminated with ethylium bromide. Ethylium bromide is a mutagen.
Oh,
so it's better to wear gloves.
Yeah, I remember they told us that. Yeah, one of the stuff we were using is a carcinogenic.
It's not 100% proven that it's a carcinogenic, but since it interacts with DNA, it's better to be safe than sorry. So this is the comb we use. So this is for making those wells that I talked to you about. That's where you're gonna put your DNA. So basically what you're making is jello. So that's the easy way to see it. So the way these things work, you put it this like on the side. Usually, if you get it wet, better because it lubricates the rubber. And see, if you don't lubricate the rubber, this is what happens. And if you pour your gel here, it's gonna leak.
Okay.
So you put it that way because if you see the gel beds, they have walls on the sides, but not here. So you want to cast your gel in here. So the way to do it is just put it that way. So you block this wall right here. So there are several systems. This is the one we use, and it's pretty convenient. Then you put your comb. That's how we call them, comb. So see, this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 samples. You can run 12 samples in this gel. If your product is small, you can run another 12 down here, but we usually don't do that. It's better to have longer gel, to run it longer and get better resolution. So in this case, you're gonna run, let's say, 12 samples. If you need to run more samples, what you can do is jump to this size. So we have all the things are here, all the gel beds are here. So see, this one fits here. and then you have bigger combs like this one. So this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This has 14 samples. This has 12 and this 14 is not that big of a difference, but if you need 2 more samples because you have 14 samples, it's better to use this one.
Gotcha.
And then you have the big one. See, this goes right here the same way. And you have the bigger comb. You can see you have more samples. So you have more samples than 12 or 14. You can run a big one. Usually, the most common one that you're going to use is this one. But the concept is the same for all of them. So now we know that we can go to volumes. So one of the most confusing things when I first started doing gels is like, how much do I need to add to make a gel here? The standard is, for this one you use 50 milliliters, for this one you use 100 milliliters, and for this one you use 150 milliliters. So 50, 100, 150. That's like the most you want to put. There's people like me that this one can take from 30 to 50. So from 30 to 50 milliliters you're gonna be fine. I usually do 30, so that way you get a smaller gel, you use less material, and it's a preference. I prefer to do it with 30. There's people that prefer to do 50, and you can even put more, but more than 50 it's useless because it's going to be huge gel. There's no point in having that.
Right.
So now we're gonna make gel. So again, 50 and 100, 150.
Okay.
This setup, right? You can see that it's ready to pour gel in here. Let's go. So the way we do a gel, we grab one of these bottles right here. A lid or a cup. There you go. So we're gonna use this one. So this is how much volume?
50.
50 milliliters. So the gels that we use for DNA they range. So gel concentration. They go from 0.8% to 1.5%, pretty much. The standard is 1%. If you go below this, the gel is going to be very liquid and flimsy, and it's not good. If you go above this, the gel is going to be very rigid, and your DNA samples are not going to run very well. So there was, depending on the size that you want to run, so bigger bands you want to run them in this concentration, smaller bands you want to run them in this concentration, but in general you just use 1%. So this 1% is weight in volume. So basically, if you want to make 100 milliliters, 100 milliliters of 1% gel, you add 1 gram of agarose, right? So in this case, we don't want to make 100, we want to make 50. So for 50 milliliters of 1%, we need to add 0.5 grams of agarose. Does that make sense to you?
Yes.
Fair enough. When you make Jell-O at home, you need water, hot water, and you need Jell-O, right? The agarose is our Jell-O, and we don't use water. We use buffer. Remember the buffer you made the other day?
Yes.
We use buffer because buffer has salts and allows the current to go through the gel, as well as the running buffer has the same buffer, so the current can go through. You can you can cast it with water. Like you can do it with plain water, but it's not gonna work. It's gonna melt because water doesn't have enough electrolytes to let a current go through, so it acts as a resistance. So the gel is gonna get hot and it's gonna melt. It's no good. It's a common mistake to do with water, at least once. It happened to me several times. You're gonna just ruin the whole thing. You're not gonna be able.
It's gonna melt.
It's gonna melt.
Oh.
And it's like you'll have to repeat
right.
it. So use buffer. So we use this to measure the buffer. So we need 50. This doesn't need to be exact. As long as you have somewhere around 50, like that. So I went a little bit over. It doesn't matter. We put that. And then we need to weight the agarose. So here we have agar and agarose. Agar is for media, agarose is for gels, and I'm going to show you the difference. This is how agar looks like. So it's like flaky, yellowish, coarse, and this is how agarose look like. Fine white. So they are the same thing. This is more refined. See? Then you can see the refinement right there.
Yes.
You could run a gel with this. I never tried, and I don't know what would happen, but technically you could. It's not the best practice. So you can throw this away. So we need 8 point. Again, I'm using the paper because I prefer to use a paper in this case. So we need to weigh 0.5 grams. Again, this doesn't have to be very exact. So in the with the buffer, I pour a little bit over 50. So if you go a little bit over 0.5,
it's fine.
It's fine, yeah. See, that's good enough. Agarose, it's kind of expensive. It's not extremely expensive. Yeah, well, yeah. So this thing, it's $1 a gram. This is 500 grams. So this is $500.
Oh god.
Yeah. In that sense, it's expensive, but 500 grams go a long way. You can be working like 5 years with that.
Okay.
You're not gonna run out because you know this is what.
You only use small amounts, okay. But still.
Still, yeah.
Don't drop the bottle.
Yeah, exactly. Like if you mess up a little bit in your paper, the best thing to do is not put it back, just throw it away. Because if you contaminate the whole thing.
Yeah, it's $500.
So now we have that. So like Jello, we need heat now. So with Jello, you just pour boiling water. In this case, you just pour it first and then you boil it. This is very important. The lid should be loose,
right?
Because otherwise, it's just a pressure bomb,
right?
And we had a couple undergrad students. So there was another grad student that was teaching them to do this. He forgot to mention that, and they were making a gel by themselves. And I was in my bench, and I started hearing the rattling inside the microwave. I'm like, what are you doing? We're melting a gel. And I see the bottle is rattling all around. I opened it. The lid was shut, like sealed, tight. I took it out. I opened it, and a cloud of steam like
just came out.
And they freaked out. I mean, it could have blown, but yeah. So the best way to do it is just open the lid and let it go. I like, some people put like 1.5 minutes and walk away. I like to be present and see what's going on with the gel. Like right now it's boiling. I stop it. See, and I let it sit for a couple seconds. Then put it back. See, it's boiling. Let it sit for. So use gloves whenever you need to handle hot stuff. It's very So right now I don't know if you see like clear balls.
Yeah.
That's unmelted gel, so you want it to be clear as water.
Okay.
So put it back. Maybe. So that was a minute. So it doesn't take long for it to melt.
Mm-hmm.
So 15 seconds.
You just previously put it up to 15 seconds as well.
So the first time I put 1 minute.
Okay.
And I was checking it at when it was like 15 seconds left, it started to boil. So I opened it just to see it, to let it sit for a while. Then I closed it back again and started. And that, so that you can walk away. Some people walk away. I don't like to walk away.
Right.
So now it looks fine. So now, while you're not applying heat, you can shut the lid. It's fine.
Okay.
So I don't see any more balls around. Oh man, it's hard. And that's pretty much it for. So it was relatively easy.
Okay.
So now we need to add the stain. So as I told you, we use ethylium bromide. There are safer chemicals that you can use, but we don't have the equipment to see it afterwards. So that's why we keep using ethylium bromide. In the future, it would be nice to have cybergreen or something else that works as fine as ethylium bromide. So this is the ethylium bromide we use. This one is empty. You have to dispose of that. These are the tips we use for ethylium bromide, because you have to dispose it in a special way. So we just keep it here.
Right.
So what you're gonna do is you're gonna have your ethylium bromide. Wear gloves at all times. What we usually use, it's 1 microliter per 15 milliliters. That's what I use. There's people that use more. There's people that use less. That's the concentration I'm comfortable with, because I know it works and I know it's not too much. So what you do, you get your pipette, put in 1 microliter. This is a 5.5 to 10 microliters. So put it to 1. Then grab your tip. So you well, I messed up. So you open the bottle. You take. See, it's very little. You put it in your thingy, in your gel. So it's almost nothing. You put your tip in here, and then you want this to mix. You mix it a little bit. And that's it. You let it sit for a couple of minutes. Then you clean these because it has alcohol properties, so it cleans very well with ethanol.
Like dissolves, like.
Yeah. So we close these. That's it. And then as we go to hazard waste, is the box in here. So this box right there with the red bag, it's hazard waste or whatever.
Got it.
So this is pretty much done.
Okay.
Now what we're gonna do. I think this one works. Yes, this one works. So you have your gel bed, your comb, everything set up. So what you do next is you get your gel in the bottle and you pour it here, like that. As easy as that. So see, it's clear. When it solidifies, it turns like whitish. So you put this, because this is hot, it's going to be evaporating. So you have ethylium bromide and you don't want to breathe that. So you put the lid and let the condensation get like get the lid trap all that condensation. What I do sometimes is sometimes you're gonna get bubbles. I just shake the gel a little bit like that, and that should get rid of the bubbles. And then you let it sit until it solidifies. Once you're done with this bottle, it has a little bit of gel left, and this is gonna solidify. If it solidifies inside the bottle, it's very hard to get it out, and that would be a lot of work for you because you're the one who does the dishes.
Right.
So what we do while this is still hot, we just put high pressure water like that, and that's gonna get rid of most of the gel. Like this is pretty much clean right now. You don't have to clean it further. Rinse it a couple times. And that's it. You don't want to let that solidify inside there because it's a pain about to take it out. So that's pretty much it for the gel. Now we're gonna prepare some samples for you. So these are PCR reactions I ran a bunch of time ago. They have been in the fridge. Probably have around like 2 months. They should be okay. So that tells you that DNA is very like persistent. It doesn't degrade very fast. I'm gonna run these three samples. So the reason I spin them down is because they were like, sometimes they evaporate to the lid and you have to get it down. Okay. So let me see how my gel is going here. If you want to see. So remember that I put my samples in here, like in the wells,
right.
And now they're like that way, so it runs. So we add a dye. The dye is not necessary, but it's necessary for you to see the running. Where is it at? So usually I wait until the blue stuff is up to here, and once it reaches this point, it's done. So it needs a couple more minutes. I'm gonna crank it up a little bit. Okay, so we're going to run 3 samples. In this case you have like 12 wells. We're not going to use all of them. We're going to use 3 samples and we're going to run a benchtop ladder, but we're not going to use this one. Well, we can use this one and the other one so you can see how they both look like. And you're going to be the one loading the gel. Do we have one? I guess we do not. We don't have the other ladder. Doesn't matter. We need to purchase it. Okay, so as you can see, our samples are clear. They don't have any color in them. So if we load them, we're not gonna see them, right? So that's why we add loading dye. This is loading dye. You just purchase this. It comes like that. The other reason we use loading dye is because loading dye has glycerol in it. Glycerol is very dense. So if you put glycerol in water, it's gonna sink. So whenever you put your running buffer in your gel rig, it's gonna be all water, basically. If you add your sample if you, let's say we add some color to this, just some dye. If you put that in the gel, it's gonna diffuse out because water mixes with water, and that's what happens. It diffuses out. When you mix your sample with this that has glycerol, the sample becomes dense, and it's not gonna like
move as much, disperse.
Yeah, it's not gonna disperse. It's gonna
sink right
to the bottom. Exactly. And this has dye already in it, so we don't need to add dye to this. So the way to prepare the samples. Let me see. One thing I don't do this much often, but since we're doing this just to see it's not gonna hurt it, I put this in the fridge for a little while, so it solidifies faster.
Got it.
Normally, you should let it sit and go do something else, and come back later because it solidifies better that way.
Today we're just running practice.
Yeah, we don't run any practice, exactly. So now you're gonna prepare the samples. You're gonna do this. I'm gonna show you one, and you can do the other two. So we use this. This is par film. We use this for several stuff. Like you can seal tubes with it. Let me show you, for example. Have you ever used this stuff?
I don't think so.
So this is basically wax, like
wax paper. Okay.
Yeah. So let's say you want to seal this tight. So you grab it like that.
Ah.
Well, you understand the concept, right?
Yeah, it just keeps the air out.
Exactly. So you can do that. It works really well in summer because the air is warm.
Humidity, yeah.
During winter, it's more brittle and it breaks.
Oh, okay. It's the
if you heat it with your
temperature.
hand,
Okay.
Yeah, yeah. Because it's like if you put this in a flame, it's gonna melt, like wax. Pretty much, it's wax. So the other thing we use it for is to prepare samples for DNA, for gel. So what I do, I cut a little bit. So it depends on how many samples that you have. You're gonna cut as much as you need. In this case, this is too much for 3 samples, but that's fine. What I do is put it in this thing, and using gloves, I just press on the holes, and this is gonna create like a well. So this is gonna be like, there's people that don't do this. They just use paper as it is. I prefer to do this because that keeps your sample from mixing with each other. It's more clean for me. And I showed this to a bunch of people in the lab, and they really liked it, so now they use